Swayam Prabha. Digital India. Educated India.
Welcome back to infrared spectroscopy. We're going to look at a new functional group that has OH bonds. How do you recognize them in infrared spectroscopy? One of the distinct features about OH bonds is that the peaks are broad. Again, OH has very low mass, therefore your wave numbers are high and they will be about 3000. Now, you have OH in two functional groups. One's alcohol, one's carboxylic acid. Okay, we do have other ones like enols and so on, but the most stable ones are typically alcohols and carboxylic acids. And that's what we have here. This is an alcohol. I know you only think of, your beer and wine when you think alcohol, but we have thousands of alcohols, even sugars are alcohols. And a lot of them are solids. Carboxylic acid, again, you might think of acetic acid, which is your salad vinegar, but a lot of them, especially above 5 and 6 carbons, are solid carboxylic acids. And typically, you can grind it up with KBr or sodium chloride and then put them in the infrared and get spectra. If it's a liquid, you can put a drop on your KBr pellet and then make sure there are no air bubbles and then put it in the IR machine and you get this nice spectra, FTIR spectra. So here we're going to look at what these peaks mean. You're seeing a lot of spikes here coming down. What does that mean? How do you know that's an alcohol? We'll do what we did earlier, which is filter out your alkene, because all hydrocarbons will have the same type of CH stretch and CH bend. So take your alkane spectra, overlay it, so we don't have to then worry about what these peaks are and what these peaks are. Let's look at the rest. All right, so now this becomes really very prominent. You have a very broad peak here. Why is it so broad for hydroxyls, where a CH was real sharp peaks? You got CH for triple bond, like almost like a line, and CH2 really sharp. Why is it that OHs are so broad? There's a unique feature about OH bonds, and that is, right, hydrogen bonding. OH bonds have hydrogen bonding, which means they are bonding to all of their neighboring molecules. Now, if you have a lot of hydrogen bonding, then your OH bonds have lone pairs here. The lone pairs are attracted to a hydrogen, and then that lone pair here is attracted to more hydrogens, and it keeps going on and on. It's, all throughout the solution. It's all because it's oxygen's very electronegative, hydrogen's a teeny atom. The electrons are sucked in towards the oxygen. It's very polar. And polar bonds tend to absorb in very high intensity on infrared. So you can see that bond it's always, OH bonds are very, very intense. That means your absorption is almost 100%. Okay, in this case, about 80% absorbance, 20% transmittance. Okay. So the hydrogen bonding here is going to create varying lengths of OH bonding. So therefore, you're going to see a lot more variation in the bonding, bond length and bond strength. So you have a lot more transition possibilities. It's not going from one in a CH bond from one to another level. And we talked about that. You can have your vibrational frequencies and then your rotational frequencies in between, and they can go, from one to the other, or go over here, and there are lots of variations. So you have a broad spectrum of absorption due to the variation here. Usually there's OH, there's only one bond there, so you don't get a doublet or a triplet. You get a nice single peak, but it's going to be broad. Now, if you have a very, very dilute solution, and let's say you have it in a solvent that doesn't hydrogen bond, you will get a sharp peak for OH. because you're minimizing your interaction with the neighboring OHs. All right, but typically the regular concentration that you do your infrared in, you are going to get a lot more hydrogen bonding. All right, so these we know are the CH of the alkanes. So your R groups here will have CH2, CH3, all of those. And this is going to be your bending for your R group. Now, this is something that's not in an alkane, so this is unique. Well, what else does a alcohol have? So if you take an alcohol, you can have RCH, OH. This is your OH bond here. And you can have a CO stretch as well. And all of the CCs will also be there. And as I said before, CC, single bonds are hard to see. So you would typically see a CO and an OH for an alcohol. OH, we already said, was this. This is our OH stretch. And the OH stretch is pretty broad. It's between 3,400 and 3,300 typically. Now, the CH of a triple bond also absorbs around 3,300, but it's really sharp. So that's how you tell the difference between an alkynic CH and an alcoholic OH. Broad because of hydrogen bonding. So let's look at this region here and see what these are here. So they are CO bonds. And this is the OH bond. So you have two types of stretches in an alcohol. You have OH, which is this, and which is over here. And we have CO. Now, CO stretches are typically in this 1100-ish, 1200-ish region. So this is going to be your CO stretch. And CO stretch, you have multiple peaks here, and the frequency depends on whether it's primary or secondary, where you have two R groups and just one hydrogen, or tertiary, where you have three R groups and no hydrogens on that carbon that's bearing the oxygen. So that is going to be tertiary. You can also have phenols. And phenols are basically alcohols that are attached to a benzene ring. All of these have their OH stretches in this region. Let's look at the CO stretch regions. Okay, so CO stretch here, primary is going to be less than secondary, less than tertiary, and that's going to be less than phenols. All right. Now, the whole stretch is between 1,000 to 1,250, and they're medium. These are strong. They're coming all the way down. Okay, so these are going to be strong and broad. These are medium, and they are not really broad, medium here. All right, let's look at our CO stretches. What kind do we have? If you are a primary alcohol, you'll be between 1050 around, typically, to 1085. If you're secondary, you're going to be 1085 to 1125. So this is where you're going to look to see what these are. This is going to be a primary because it's right here at 1050. Okay. Now, if you're a tertiary, you're going to be 1125 to 1200. So there's really very nice regions that don't really overlap, and they're slightly shifted to the left as you go from primary to secondary to tertiary. The phenols are a lot broader, above 1200, and typically below 1800. That's for phenol. So looking at these regions, you can predict where the OH group is situated in the molecule. I mean, whether it's primary, secondary, tertiary, or phenol. Now, over here, it's hard to tell what these are. I mean, they're probably OH outer plane, bending is in here, and so on, but we don't usually use that to identify the functional group. This is a saturated alcohol because we don't see any absorption at around 1600 for double bonds or 2200 for triple bonds. So we know it's a saturated alcohol. Now we do know that it has got a CH3 and a CH2, because if you only had CH2s, let's say it was cyclohexane, then you would see single peaks, not double peaks, because you only have CH2s and not CH3s. So this probably has some methyl branches or methyl groups. All right, so that's pretty much all the information we can say, and we can say it's a primary because it's at 1050. All right, so that much information we can get from an infrared. We really can't go into how many carbons there are or what exactly is the structure of the backbone of this alcohol. All of that information would typically come from NMR, which we're going to look at later. All right, okay, hang in there, guys. We will get to that sooner than you think. Let's look at another type of OH bond, and that's found in carboxylic acids. Again, let's do the same thing we did earlier, so we can at least try to minimize the number of bonds we have to go in and decipher and assign, because we know that this is your CH stretch, this is your CH bend, and here's a CH2 rock. So we know that those peaks are due to the chain. Okay, now let's look at this broad peak. That's very unique to carboxylic acids. So carboxylic acids have got a carbonyl that's directly connected to an OH. Okay, the carbonyl is anywhere else in the molecule. It's not a carboxylic acid. These are connected. So therefore, you also have, you can see some resonance that can go on here. In addition to that, you can say that these carboxylic acids are going to have very, very strong hydrogen bonding. Typically, it's floating around in your solution as a dimer. There's lots of chemical evidence for that. So here is this carbonyl attracting the hydrogen of this molecule, and this carbonyl would then attract the hydrogen from this OH. So this dimerization is very common. The amount of hydrogen bonding would depend obviously on how many other molecules are in the solution that can contribute to the hydrogen bonding, and so therefore it would depend on the environment, the solvent, and so on. Typically, if you have a solid carboxylic acid, you would dissolve that in paraffin oil, and you would run that in, and you would see much sharper peaks for the OH, but it would still overlap with the CH peaks. It's just going to be a thick band here. But if you're running it as a liquid, you would see a lot of hydrogen bonding, and it'll be very broad. It's going to be between 2500 to 3500 and very broad and very strong, because it's going to come all the way down here. That's very, very unique. If you see something like that, right off the bat, you can say that's carboxylic acid. So this is your OH. All of that's due to your OH here, your OH. And your OH is going to be hydrogen bonded and in that region. All right, let's look at the other peaks here down the line, where, well, you didn't have this over here, and this is a huge peak, almost zero transmission, which is the whole thing's absorbed by the molecule. So it loves to really stretch in this region. And there's only one thing that can do it around 1700. And that is, that's right, a carbonyl. So here is a carbonyl here, and that carbonyl is going to be absorbing, because carbonyls are double bonded, so your K force constant is really strong. In addition, they're very polar because the pi is a polarizable pi because the oxygen being electronegative. So therefore, it's just drinking up all that infrared. Can't get enough of it. Okay, so it goes all the way down here. So that is your carbonyl stretch. Anytime you have a double bond to an oxygen, double bond oxygen, you'll have a very strong peak in this region. We look at some of them. So here, this is going to be about 1760 for a aliphatic conjugation there. And if you have conjugation with that, let's say you have more aryl groups, that means you got a benzene here or things like that, then you'll have a lot more resonance. So some of the time, you'll have this double bond becoming like a single bond during resonance. And so your bond order goes down, and that's going to bring down your K and your frequency and your wave number. So that is going to shift down to about 1710 to 1680. So typically this is how you would see a carboxylic acid. You'll have a broad peak here and a narrow peak here. When you see these two, that kind of nails it. Okay, there's nothing really else that does that. You can also have a CO just like here. So around 1200 is going to be your CO peak for your carboxylic acid. All right, and this is another very unique feature. You'll have a very strong around 900 out of plane bend. So over here, you are going to see this. Again, this is your CH2 bends, and we already said that, this is going to be your C single bond O right here. This is your double bond O, and this is your single bond O stretch around 1200 to 1250. And you would always have a very strong out of plane bending for the OH. But typically these are the two that we look at. You have a carbonyl and a very broad 2500 to 3500 peak. That's it. That's a carboxylic acid. Okay. These are just other things that accompany that, but that's really the proof. All right, guys. So here's your OH bonds, alcohols and carboxylic acid. This is a huge part of your food. Or your sugars are alcohols or have lots of OH groups, and your fatty acids and your amino acids all have carboxylic acids in them. So your food, the three major groups, have either this functional group or this functional group or both. All right, so that's food for you guys with infrared. All right, just a very brief summary here. So we talked about hydroxyl bonding here, two types. Alcohol, OH bond, OH peak here between 3300 and 3400, and that depends on the concentration of your sample. If you have very, very dilute or nonpolar solvent, you'll have a sharp peak. But for most alcohols, if you put a drop on your KBR palette and put it in your infrared, you're going to see a very broad peak due to all of the hydrogen bonding. Another nice thing about infrared of alcohols is looking at this peak here, the strong one here. You can say whether it's a primary, secondary, tertiary, or if it's a phenol. Okay, now how is it different from a carboxylic acid OH group? It's extremely broad, 2500 to 3500. Again, it depends on the environment. If it's in a non-polar environment, you can get a sharper band here. But if you're putting a drop on your KBR palette and putting it on there, you're going to see a lot of hydrogen bonding, dimerization, very strong hydrogen bonding. Therefore, you're going to have lots of levels for transitions, and therefore you're going to get a very big broad peak. It's always going to be accompanied by a carbonyl here, and the carbonyls around 1700 to about 1760. And then if it is conjugated, it's going to go even lower because of all of the resonance that you would see. Another thing about carboxylic acids is they're also going to see the CO stretch here, and that's actually a range 1320 to 1210. Earlier I had put a single number, but it can be in anywhere in that range, and you'll have around 900 a very kind of a broad but medium outer plane bend for the OH. All right, so I hope that would help you identify alcohols and carboxylic acids. Talk to you soon.